You can have one 4-byte number where each byte represents one channel: red, green, blue, and alpha. This is a neat trick and you'll see it quite often, especially when working closer to the metal, when you need bulk pixel operations, graphics API integration, or in scenarios where memory bandwidth is the primary constraint. In the C++ world, we are frequently obsessed with optimizations and squeezing out maximum performance. I know the current state of game development doesn't always reflect that mindset, but hey, let's be idealistic. Modern systems work best when data follows specific structures and principles. One of the most basic and important one is proper memory alignment. Also, if you are working with embedded devices, even a small amount of memory waste can be a real issue. So, writing things effectively often comes down to understanding bit operations and bit-level data access. I showed you two common use cases: how to store pixel values in a single variable, which we call packed format, and how to efficiently store multiple boolean values, known as flags. Welcome to the channel. My name is Pavel, I work in game development, and I'm a former graphics developer and researcher with a PhD in computer science. We talk here about computer science topics and interesting projects. Many programmers work comfortably with high-level data types like integers, floats, and strings, but today we are going one level deeper. We are going to explore the binary world that underlies everything your computer does. We use 0 and 1s, just these two values, which on the deepest level means, is there a voltage or not? I have more details in my series Basic Concepts of Computer Science. Let's start with basic operations. First up, we have the bitwise n, represented by the ampersand symbol. This one checks two numbers bit by bit and returns 1 only if both bits are 1. For example, if you do 12 and 25, you'll get 8. Let me write it down so you will see what is happening on a bit level. 12, 25, and this is equal 8 in decimal. Next, there is bitwise OR using the pipe symbol. This returns 1 if at least one of the bits is 1. So 12, 25, give us 29. Then we go to bitwise XOR, shown as caret. This one's all about differences. It returns 1 if the bits are different. Try 12, 25. The result is 21. Now the bitwise NOT, written as tilde, flips all the bits. It's like turning every 1 into 0 and vice versa. But here's a twist. Because of how negative numbers are stored in binary, the tilde 12 actually gives -13. Moving on to shifts. They are about moving bits left or right. The left shift pushes bits to the left and multiplies the number by 2 for every shift. So 12, shift left 2, becomes 48. Right shift moves bits to the right, which is like dividing by power of 2. 12, right shift 2, gives you 3. Don't forget that we group 8 bits together and we get byte, which can represent 256 values from 0 to 255. In graphics programming, bit manipulation is essential for efficient color handling. As mentioned, colors are often represented as 32-bit values, where each 8-bit channel represents a red, green, blue, and alpha components. We pack all 4 components into a single integer using bit shifting. It looks like this. First up, R left shift 24. This takes the red value and shifts it 24 bits to the left, placing it in the highest 8 bits of the 32-bit number. Then G left shift 16. Green gets shifted 16 bits, so it sits just below red. And B left shift 8 is shifted 8 bits, sitting below green. And finally, A stays as it is. The pipe operator, which is bitwise OR, combines all of these into one tidy 30-bit value. So now you've got a number that holds all 4 color components, perfect for graphics, pixel manipulation, or shader programming. The second example is about flags. A flag is essentially the state of something at a given time, such as the state of a player here. He can be alive, invincible, and flying, or he can be alive and poisoned. As you can see, these are essentially booleans. Is he frozen? Yes or no? But if we define an array of 6 booleans, see what happens in memory. We are using 6 bytes for that. That is already wasteful. So if memory consumption is an issue for you, check this. Think of state like a set of switches, each representing a different ability or condition the player can have. The player starts out alive, which is the default state. The class offers a few handy functions to manage these states. Make invincible. Turns on the invincibility by using a bitwise OR. This means the player becomes invincible. Remove invincibility does the opposite. It turns off the invincibility using bitwise AND combined with NOT operation, making the player vulnerable. Is invincible checks if the invincibility switch is currently on, returning true if the player is invincible, and false otherwise. Finally, toggle flying flips the flying state on or off using a bitwise XOR operation. So if the player is flying, coding this will make them stop flying, and if they are not flying, coding it will make them start. You can use this approach for all states you need, or make it general for any incoming state. To me, this has always been an interesting topic. I believe that if you are a C++ developer or generally working in an environment where low-level performance is crucial, these are things you should definitely know. Thanks for watching. If you like what you saw and want to see more in the future, hit the subscribe button, and I see you next time.